The Kepler mission has observed thousands of stars in our own galaxy, and astronomers have found from the data that about half the sun-like stars it has seen have a planet orbiting close to the star, comparable to Mercury's orbit or closer. Most of these close-in planets are what they're calling super-Earths, planets that have a radius of 1 to 4 times our own and a mass of 2 to 20 times our own Earth's. Analysis of the radius and mass of these planets has revealed that they have a significant atmosphere, also known as a gas envelope, around their cores, of about 1% mass fraction. For comparison, the Earth's atmosphere mass fraction is about 10 to the negative 6, so these super-Earths have quite a significant atmosphere. This consistent 1% gas-to-core mass ratio is peculiar. Why should these super-Earths all have about the same ratio of gas surrounding their cores? They come from random nebular compositions. Some come from nebulas with a lot of gas, others from nebulas with very little. So why do they end up with about the same proportion of gas? This creates what is called a fine-tuning problem. There seems to be the need for a very specific set of conditions in order for the super-Earths to form with the observed atmosphere masses that we see. Science does not like fine-tuning as an answer, and as it turns out, it isn't. There is no exact nebular composition needed, and no required timescale for them to form either. The existence of the 1% gas ratio of the super-Earths is independent of the nebula it is born in. So how is this the case? The reason is that planets can only accrete gas to their atmospheres as quickly as they can cool down, since cores of young planets are quite hot from the accretion process. Heat leaving the planet as radiation effectively slows down the rate at which gas can fall into the core. This means that planets and nebulas with a lot of gas initially accrete it quickly, but the heat from doing so causes further accretion to be a very slow process. Likewise, planets in low-gas nebulas accrete slowly over a long period of time, since not as much heat is continuously produced. To get more scientific with this, the planets can be thought of as somewhat star-like in their atmospheres. Since the cores are so hot, their atmospheres, or envelopes, have a convection layer and a radiation layer, like our Sun and many other stars. The convection layer exists because the rate at which the radiation layer can transport heat away from the planet is controlled by the Stephan-Boltzmann equation. If the rate of heat needing to leave the core is greater than allowed, the gas acts as a liquid and columns of hot gas from close to the core rises to the radiation convection boundary, radiates its heat and cools, and then sinks back to the core, creating a churning layer of gas. This convection radiation system is a reason that super-Earths tend to have gas ratios of about 1%. Gas-rich and gas-poor nebular super-Earth hosts end up balancing by this mechanic to end up with the same observed result. That's the explanation, but there's a problem with it. The models astronomers use for core accretion relies on the assumption that the gas in the region is optically thick, meaning here that on average a photon cannot exit the region in a straight line without interaction with some dust particle. Super-Earths form in regions that are mostly depleted of gas compared to a rich, full, new nebula, since they are so close to their host star that is much more massive and that has already accreted or blown away much of the material around their young planet. This means that the region around them is optically thin, not optically thick. There is a solution, however. The four base equations of stellar evolution can be solved for an optically thin regime using more complex methods than the usual optically thick computations. The four equations involve mass, pressure, optical depth, and temperature, all with respect to radius from the center of the planet. There are a lot of details, but some notable ones are that the heat comes from both the hot core of the planet and from the host star that is not all that far away. Another is that the ratio of optical depths of visible light to thermal radiation is very important in the optically thin case, and is determined by the two heat sources mentioned, the star and the planet's core. The overall method to solving the stellar evolution equations for the optically thin case involves guessing starting values, working with those guesses, seeing if those guesses were actually good or not, and so on. Bad guesses mean starting over. As it might sound, the optically thin case is indeed more intensive to solve than the optically thick one. The results of the calculations show that the composition of the nebula that surrounds the planet has only a minute, but proportional, effect on the resulting gas-to-core mass ratio of that of the mature planet, as observed with the Kepler mission. The result is even rather independent of the ratio of the optical depths. That is, the host star can have a large range of temperatures and fluxes that reach the planet before there is a significant effect on the amount of gas that the planet accretes. There is a limit found with the calculations, though. If the nebular gas composition is too low, the model breaks down. This is because, in the model, the radiation convection boundary will have been pushed inward almost exactly to the rocky core surface. In this case, the model sequence dies. Thus, while it may have seemed strange and in dire need of a fine-tuning solution, there is no trickery for super-Earths close into their stars, having quite substantial uniform gas ratios of 1%. They will form this way no matter the composition or timescale, or even stellar temperature, to within a reasonable constraint. Science saves the day. When I initially read this article and started reading about these atmospheres, this was something I had never even thought about before, and reading it, as they lay out the problem of the observations, I was like, yeah, what the heck is going on? Um, but yeah, I really believe in this article and what these people have done in order to do the calculations and the math and the models. I find it really assuring that this is what happens and the math works out and they're, the results are good. Especially since the results do still show a small but proportional resulting gas ratio to the nebular composition still. That's also reassuring that, it's not just bogus results. There is still this proportional effect, but it is very small, and that was very cool to see. So, I hope y'all enjoyed. The original paper was called Optically Thin Core Accretion, How Planets Get Their Gas in Nearly Gas-Free Disks, and the authors were Eve J. Lee, Eugene Chang, and Jason W. Ferguson. Oh boy. The overall method to soiling, nope, that's not right. Thermal radiation is very important in the optical. I read that right. Why am I pausing? Why am I doing this?